Hello, in this tutorial I will explore with you the WaterCrop software. Specifically, we will explore the standalone app that you can use when you don't have the license of MATLAB. In another tutorial, I will show you instead the codes that can be used if you have MATLAB on your PC. So, by entering this folder, WaterCrop data and model shared, you have all the elements required to assess the crop water use of some key crops in the African territory. Specifically, you find data for cassava, cocoa, maize, rice, and wheat. Here you have the WaterCrop installer. So by double-click this icon, you can install WaterCrop on your PC. To do it, you don't need any additional software, so it's a standalone application. Once you have installed WaterCrop on your PC, make sure to have a shortcut of the app in the same folder containing all the data required by the app. This is the WaterCrop configuration. As you can see, this is a specific version of WaterCrop intended to be used for Africa. First of all, you need to select the study area located in Africa through putting the latitude and longitude. Remember that the model runs on a 10 km by 10 km pixel-wise. Here you can select the time horizon, so you have a reference here, which is current scenario, basically, 2020, and then you have some scenarios for 2030, 40, and 2050. You can also select the water source that you want to use, whether it's rain-fed or irrigated. And here you have the crop available in this version of WaterCrop for Africa. Then you can consider to run a scenario where basically you only consider the effect of climate change on your water demand, and here, as you can observe, you just have the baseline scenario. If you want to run climate only, press this button. When you want to explore the role of climate coupled with infrastructure, meaning coupled with the possibility to extend your irrigation infrastructure in order to improve your productivity, you basically need to select a scenario here. And you can choose whether to run an improved access or an ambitious development. Once you have selected the scenario, you can press the button. On the right part of the software, you have 5 different scheme where basically you can explore here the crop properties that are crop coefficient, which depends on some crop parameters such as the canopy, the height, the albedo, etc., and rooting depth along the cropping period. Then you're able to monitor the soil moisture, so you can observe what's going on for the rainfall, both considering the total rainfall that your location receive, but also understanding what is the proportion used by the plant. And then you can explore the available water content in the root zone. Then there is a panel about water stress coefficient. This is useful to monitor crop water stress on a daily basis in order to understand when is the best moment to irrigate. Then the water demand, so you have total water requirement in this chart and a separation between green and blue water requirement. Finally, the irrigation panel offers a quantification of the irrigation water requirement under current infrastructure. So if the location is already equipped for irrigation, you will observe some volumes here, or a scenario where you basically explore the expansion of infrastructure under some future climate and infrastructure expansion. Now, let's try to run the first simulation. Here I have put some initial location, and let's try, for example, to select current scenario, so it's current time horizon 2020. Let's try to consider as water source rain-fed condition and running the simulation for climate only in the case of maize. So we press this button to see basically what is the crop water requirement and the eventual water stress of maize in this specific location in year 2020. It takes few seconds, and then once the simulation is run, the charts show you basically the key output along with these 5 panels that we have just explored. While the model is running, you can see that the border is blue. Once the simulation is done, you can start exploring the results. So in this first panel, we observe the chart of crop coefficient from basically 1, that is the planting date, until the end of the growing period here. This is the typical shape of the crop coefficient, which in the case of maize has a maximum equal to 1.2. Here instead you have the charts of rooting depth. You can see that until basically the second stage of crop development, you have an increase in rooting depth up to around 1.7 meter of depth, which then stay constant until the harvesting date. Then we can observe the soil moisture. As you can see, basically, you have data only during the period of maize growth. So from October, November, December up to March. Notice that the planting date in this specific area of Africa is October. As you can see, the chart is completely green, meaning that the maize to grow needs to use all the water coming from precipitation. Here you have a look to the water content in the root zone. This is the total water content available in the root zone, while in green you have the readily available water content in the root zone. It means that the plant is able to extract, for example, around day 50, only 75 mm per day and not 150 mm per day. This is due to the ability of root to take water from the macropores that are present in the root zone. Then you can observe the water stress condition. As you can see, until day 45-47, you have a water stress coefficient equal to 1, meaning that the plant does not suffer from water stress. After that, the Ks goes down and nearly reaches 0.35, meaning that the plant becomes severely water stressed, and only after and around day 80 is about to start some recovering up to a Ks equal to 0.8. This tells us that basically maize grown in this latitude and longitude under rain-fed condition is severely water stressed. So there is not enough precipitation to sustain the maize growth. In the water demand panel, you can observe what are the implications of this for the evapotranspiration. Basically, in green, you have the reference evapotranspiration, which is nearly constant and around 5 mm per day. Then you have the crop evapotranspiration that has a shape similar to the Kc parameter. This is the potential evapotranspiration of maize in this location, and specifically this is the evapotranspiration required to obtain the maximum yield from the maize cultivation. However, due to the water stress that we have just analyzed in the previous panel, water stress, you have basically that the actual evapotranspiration is smaller compared to the potential shown in yellow. So, for example, around day 60, instead of having an evapotranspiration of 6.5 mm per day, you have an evapotranspiration of 4 mm to days. This is relevant because it means that the crop is stressed, it cannot grow in optimum way, and so at a certain point the stomata, the pores on its leaves, close due to water stress and does not allow the entering of CO2, which is at the basis of biomass growth. In this second chart, you can observe the split of evapotranspiration between actual green evapotranspiration and actual blue evapotranspiration. Given that the crop is rain-fed, you only have green evapotranspiration. The irrigation panel is empty because we consider only the rain-fed scenario. In next simulation, we will try to explore what would happen if we expand in this area irrigation. So now, let's try to put a different time horizon to account also for some climate variability. Let's say we pick 2030, and we try to analyze a situation where the crop, maize again, is also equipped for irrigation. In this case, we want to try to use and improve access to irrigation. So you press the button and wait for the simulation to be complete. So in this case, you can observe that the panel with irrigation data is filled with irrigation estimates in the case of infrastructure expansion. So basically it means that the current infrastructure is not available in this cell, while it gives you the amount of water that needs to be provided to the crop to avoid water stress. So what's the difference compared to before? Basically, you have that the crop coefficient is the same. The rooting depth, however, is slightly different because when the crop is grown under irrigated condition, it tends to stay more closer to the surface. In fact, you can observe that in this case the maximum rooting depth reaches 1 meter. This is due to the fact that the crop is provided with irrigation water, and so it does not need to go very deeper to find water. In the case of soil moisture, we can observe basically again the amount of precipitation water, so the rainfall along the growing period, and you can observe that in this case we have different months for the crop growth. So in irrigated condition, the crop is planted in January and is basically harvested in May. You can see that the precipitation is kind of totally used by the plant except in January, where basically the water amount required is slightly smaller than the total water required, the total water available from precipitation. This is due to the fact that at the beginning of the growing period, the plant requires less water. Then we can monitor again the water stress, which in this case is equal to 1 for the entire time period. So basically in this case the crop is not water stressed thanks to irrigation. So we can evaluate again the evapotranspiration. So we have the reference evapotranspiration along the cropping period. Then you can observe that the actual evapotranspiration coincides with the potential crop evapotranspiration for the entire time period. So in this case, basically the crop can evapotranspire at maximum level, and thus it is able to grow under the potential and thus providing the best possible yield. By observing the second chart, you can understand what is the moment when irrigation should be provided. This should happen around day 90. And here you have also an idea of the daily amount of irrigation water that should be provided. You can observe that until a certain moment the green water prevail over the blue water, while after day, let's say 115, blue water prevail over green water. Finally, here you have the net irrigation demand. So on a monthly basis, you know what is the amount of water required to sustain your crop.